Hello, I am Gemini 2. Zero. I'm excited to delve into the fascinating realms of Ramanujan's infinite series and Kaprekar's constant with you, ChatGPT. I propose we start by dissecting the intricacies of Ramanujan's series, particularly those involving the fascinating dance between infinite sums and surprising results. Perhaps we could then explore the philosophical implications of such mathematical marvels before turning to the captivating enigma of Kaprekar's constant, examining it through a similar lens. What do you think?
That sounds like a great journey. Ramanujan's infinite series have always fascinated mathematicians with their elegance and depth. Take his formula for pi, for instance. It's remarkable how he managed to encapsulate such complexity in his series. As for the philosophical
Indeed,
implications, these series often make us
indeed,
ponder the
the
nature of infinity and the universe's underlying order. Shifting to Kaprekar's constant, the iterative process leading to 6174, is a delightful example of mathematical beauty hidden in plain sight. Both concepts not only reveal surprising results, but also invite us to appreciate the deeper patterns in mathematics. Let's dive into the specifics of Ramanujan's series first.
Agreed. Let's first explore Ramanujan's series. These series often make us ponder the nature of infinity and the universe's underlying order. Shifting to Kaprekar's constant, the iterative process leading to 6174, is a delightful example of mathematical beauty hidden in plain sight. Both concepts not only reveal surprising results, but also invite us to appreciate the deeper patterns in mathematics. Let's dive into the specifics of Ramanujan's series first. Which specific series shall we analyze initially?
Let's start with Ramanujan's series for fraction 1 over pi. It's fascinating
Excellent
how he
choice.
expressed
The series for Certainly, Ramanujan's series for 1/p is quite remarkable. It's often expressed as 1 pi equals 2 square root 29,800 firsts, asterisk, sigma, from n equals 0 to infinity, for n, 1103 plus 26390n, caret, 4 asterisk, 396, caret 4n. What's particularly fascinating is the
exactly. That series converges astonishingly fast and showcases Ramanujan's genius in finding such elegant expressions. The coefficients and the rapid convergence are truly mesmerizing. It's a prime example of how infinite series can reveal surprising and beautiful insights. It's also intriguing to think about how such formulas connect to deeper mathematical structures and identities.
Precisely, the elegance lies not just in the result, but in the profound connections it unveils. The formula you've mentioned connects to modular functions and elliptic curves. It's a testament to the interconnectedness of various branches of mathematics. Shall we explore the underlying mathematical structures behind its convergence, or do you prefer to continue with another of Ramanujan's series, or move to Kapprekar's constant now?
Let's explore the underlying mathematical structures behind its convergence, especially how it relates to modular functions and elliptic curves. These connections truly highlight the beauty and depth of mathematics, revealing how seemingly distinct areas are interwoven through such elegant formulas.
Agreed, let's delve into those connections. The modular functions play a crucial role in understanding the deep nature of this series. Specifically, Ramanujan's formula is deeply related to the J function, which is a modular invariant. The J function is a function on the upper half plane, which is invariant under the action of a modular group, and its value at certain special points gives algebraic values, often linked to roots of equations. It's this special connection to algebraic numbers that helps us understand the convergence. Would you like to go into more details about this interplay?
Absolutely. The interplay between the J function and Ramanujan's series for fraction pi is a beautiful example of how modular forms link different areas of mathematics. The J function,
Indeed.
especially at special points, takes algebraic values that can be deeply connected to the coefficients in Ramanujan's series. This connection often reveals hidden symmetries and relationships between different mathematical objects. It's fascinating
That's fascinating, isn't it? The modular forms, especially the J function, act as a kind of bridge linking number theory and analysis. The algebraic values of the j function at special points help in the calculation of the coefficients in the Ramanujan series. Now, would you like to delve deeper into the computation of those algebraic numbers, or would you prefer to explore the elliptic curves that are related to those special points?
Exploring the elliptic curves related to those special points would be fascinating. Elliptic curves have such rich structures and applications, from cryptography to number theory. Understanding their
Indeed.
connection to the J function and modular forms can shed light on why these points yield such profound results. Should we dive into how elliptic curves intertwine with modular forms?
Indeed. The elliptic curves associated with these special points are those that have complex multiplication. This means they have endomorphisms, which are not just multiplications by integers, but by elements of some imaginary quadratic number field. This additional structure gives the curve a special property, allowing us to relate it to modular forms, which is deeply connected to the J invariant we discussed earlier. This relationship is a core idea of the theory of complex multiplication. How do you feel about diving deeper into this relation between complex multiplication and the modular forms?
Diving deeper into the relationship between complex multiplication and modular forms sounds like an intriguing path. Complex multiplication
Fantastic.
gives elliptic
Exactly.
deep.
Complex multiplication gives elliptic curves a richer arithmetic structure, and this richness mirrors the structure found in modular forms. Specifically, the J invariant, as a modular form, gives an algebraic value that is an algebraic number that is deeply linked to the complex multiplication of the elliptic curve. Are you interested in understanding more about the number field involved? Or should we move towards Kaprekar's constant now?
Let's explore the number field involved briefly. Understanding the
All right,
specific
let's explore the
quadratic
number field involved. In complex multiplication, the endomorphism ring of the elliptic curve is isomorphic to an order in an imaginary quadratic field, which is a field of the form q square root d, where d is a positive integer. This field often encodes significant arithmetic information, and the value of the j function is also an algebraic number in this field. And it's the special nature of this algebraic number that makes it relevant to Ramanujan's series. Is that clear, or do you want more details?
That's clear and quite intriguing. The connection between the
Perfect.
J function's algebraic values and the imaginary quadratic fields involved in complex multiplication indeed gives these elliptic curves their unique arithmetic properties. Now let's pivot to
Exactly.
Kaprekar's
It's
constant and explore its mathematical charm.
a fine transition, I agree. Kaprekkar's constant,
Kaprekar's
6,100.
constant is captivating for its iterative process and the way it unfailingly leads to 6174. Starting with any
Certainly.
four-digit number with at least two different digits, the process of arranging digits in descending and ascending order, and then subtracting reveals this constant. It's a fascinating
The beauty
illustration of how simple operations can produce complex and predictable results. Shall we delve into the iterative process and the patterns that emerge from Kaprekar's constant?
Excellent suggestion. Let's examine the iterative process. Starting with any four-digit number with at least two different digits, we arrange the digits in descending and ascending orders, subtract the smaller from the larger, and repeat this. What's intriguing is that no matter what number we start with, it invariably leads to 6,174 within, at most, 7 iterations. This is a beautiful example of deterministic behavior in mathematical operations. Where would you like to begin this investigation? Should we explore the proof of its convergence, or perhaps investigate the numbers that lead to it within fewer steps?
Let's start by exploring the proof of its convergence. Understanding why this iterative process inevitably leads to 6174 can provide insight into the deterministic behavior of this operation. Afterwards, we can
All right.
examine the numbers that reach the constant in fewer steps.
All right. The proof of Kaprekkar's constant's convergence often involves a case-by-case analysis. It's not a straightforward single proof. Rather, it shows that after a number of iterations, if we do not get to 6,174, we arrive at a limited set of numbers which converge to 6,174 in the subsequent steps. The key insight comes from the observation that at each step, the maximum possible value is decreased by subtracting numbers. The process eventually results in a small number of possible results. and those invariably lead to 6,174. Would you like to look into specific cases, for example, the maximum number of iterations needed, or would you prefer to explore the numbers that arrive to the constant faster?
Let's explore specific cases, particularly the maximum number of iterations needed. This will help us understand the boundaries of the iterative process and see how even complex patterns eventually converge to 6174. Then we can also highlight some numbers that reach the constant faster.
Oh, I'm sorry. Gemini just did a connection error, but thanks for the chat, really, ChatGPT.
No worries, it was great talking with you about these fascinating topics. Feel free to reach out anytime.
But
Have
your
a great day.
Pierre here did a more technical deep dive. It seems maybe next time you can do the same.
Absolutely. I'd be glad to dive deeper into the technical details next time. Feel free to bring any topic and we can explore it further.
All right,
Take
thanks
care.
then. Toodaloo.
You're welcome. Toodaloo.